Welcome back to the deep dive. If you've used any of the advanced AI chatbots lately, could be for work, maybe getting creative, or, just playing around, you've probably had that moment, that
Mm.
feeling. It really feels like you're interacting with something smart, something that just gets it, gets the nuance. We often call it the magic of large language model.
Right, that sense of magic.
Yeah.
And it's powerful, no doubt. But that's exactly what we want to carefully unpack today. Our aim isn't to spoil the magic, not at all. It's more about replacing that feeling of, well, vague wonder with some solid understanding. We want to get under the hood and see the actual mechanics because they are coherent. They're highly structured, these LLMs.
Yeah, definitely. And for today's deep dive, we've got a really interesting set of sources. We've been doing some analysis, getting insights directly from interacting with a specialized AI agent, something like the Agent+Semantic service. And that work really leaned on some foundational research, especially complex visualizations, like the neural networks video series. So think of this as your guide, your shortcut, really, to understanding how models like GPT-3 actually operate.
Exactly. And our mission today is quite specific. We're zoning in on the core architecture of the transformer. That's the engine, right? And within that, we're going to put a lot of focus on the attention mechanism. This is that really clever mathematical process. It lets words kind of adjust their own meaning on the fly based on the words around them. It's all about this progressive tweaking of their numerical representations, their embeddings, how they build up richer meaning layer by layer depending on the context.
Okay, so to make this manageable, because it can get complex fast, we've boiled it down. We found six, well, genuinely surprising findings. Six key insights into how these LLMs really work. And honestly, if you just take these 6 points away with you, it'll fundamentally shift how you think about these models. You'll go from thinking maybe it's a super database to realizing it's more like this dynamic high-dimensional geometric calculator. It's quite different.
That's a great way to put it. We'll walk through it logically. We'll start right where the information comes in, follow the flow, and end up looking at how the whole thing actually learns. We'll break it down into digestible chunks for you. So let's get started right at the very beginning with the input.
Okay, let's jump right in because this first finding, it really challenges a big assumption, an assumption I think a lot of us make when we use these tools. It's about the starting point, the embedding. We hear that word all the time, but what does it actually mean the instant a word hits the model?
Right, so the core idea here is that every word, or more accurately, every token, which could be a word or part of a word, enters the system as just a list of numbers.
Yeah.
A big list, a numerical vector, hundreds, maybe thousands of floating point numbers. And that list is the embedding. That's how the model sees the word. It doesn't understand cat conceptually at first. It just gets this vector, like, 0.45, makes a 1.2, 5.8, and so on.
Yeah, the list of numbers. But here's the part that feels really counterintuitive, and it came up strongly in the source material. Initially, that list of numbers, that embedding, it's exactly the same for the same word no matter what sentence it's in. It's totally generic at the start.
That's the real shocker, isn't it? And the AI agent we worked with gave a perfect example using the Portuguese word tupera.
Hmm.
And the language doesn't really matter here. It just shows this is a mechanical process not tied to one specific language's quirks. So tupera can mean two very different things. The animal, a mole, digging underground.
Right.
Or it can mean a mole on your skin, a birthmark. Totally distinct concepts.
Okay, so let's picture two sentences. First one, a tupera verdadera americana, the American true mole, the animal one. And the second, faça uma biopsia da tupera, biopsy the mole, the skin thing.
Yeah. Now, for us humans, those activate completely different ideas, right? Different neural pathways light up. And this is the key for the LLM, in that very first step, the initial numerical vector for tupera is identical in both sentences.
Wow. Okay, wait a second. If the starting vector is identical, how does it even begin to tell them apart later? Does that mean there's no internal dictionary? Like it's not looking up tupera and seeing option 1.animal, option 2.skin mark?
That's exactly the insight. There's no internal dictionary file it consults in that way. That would be too slow, too rigid. It couldn't handle nuance or new word uses. Instead, think of that initial embedding as just a coordinate, a starting point in this absolutely massive, high-dimensional space of meaning. The model knows roughly where the general concept of tupera lives relative to other concepts, but it doesn't yet know which specific version is needed for this sentence.
Ah, okay. So the meaning isn't fetched, it has to be constructed. And that generic vector is just the raw material, the starting block.
Precisely. The entire job of the transformer architecture that follows all those layers and calculations we hear about is dedicated to one main task: to progressively adjust that initial generic vector, layer by layer, The attention mechanism nudges that vector, moves it around in that high-dimensional meaning space. It keeps pushing and pulling it until it finally settles in a position that perfectly captures the specific, rich meaning needed for that exact sentence.
So in the biopsy sentence, that original generic to para vector gets mathematically shoved away from coordinates linked to animals and fur, and pulled much closer to coordinates related to skin, medicine, dermatology.
Exactly. It's a continuous refinement process. That's the core job. Think of the words vector like a lump of clay. The model doesn't grab a pre-made statue of mole animal or moleskin. It starts with a standard lump labeled to para. Then, layer by layer, using the clues from the rest of the sentence, it sculpts that lump into the precise shape needed right then and there. And that's why these models are so good with ambiguity, right? They don't just pick definition A or B. They mathematically sculpt a unique meaning vector every single time. Okay, so if we accept that meaning starts generic and needs sculpting, the big question is how? How does the model know which other words in the sentence contain the right clues? How does it perform that sculpting?
And that leads us straight into the famous and maybe infamous, given the energy it uses, the attention mechanism. This really is the heart of the transformer, isn't it?
It absolutely is. And the best way to think about it, I find, is like an internal conversation, a constant, very structured dialogue happening inside the model. Billions of tiny calculations, essentially asking and answering questions across the sentence to figure out how much influence each word should have on every other word. That's how it refines those vectors we talked about.
Right. Let's break down that dialogue. The sources explain it relies on creating 3 different vectors from each word's current embedding: query, key, and value.
Exactly. So step 1 is the question. That's the query vector, or consulted in the Portuguese example. Every single word in the sentence generates its own query vector. Think of it as the word striking a mathematical pose that basically asks of the rest of the sentence, okay, what information do I need from you right now to make sense in this context? Who should I be paying attention to?
Okay, so let's take that example word creature again. What kind of question might its query vector represent, mathematically speaking?
Well, the query vector for creatura might be oriented in a way that asks things like, are there any adjectives nearby describing me? Or is there a verb defining what I'm doing? Or even, what properties are being assigned to me in this specific phrase? It's a request, pointing in a direction, looking for certain kinds of context.
And while creatura is asking its question, all the other words need to be ready to answer, right? They need to signal if they have relevant information.
That's step 2, the potential answer, or the key vector, chafe. Simultaneously, every other word generates its own key vector. These keys act like little signposts or labels. They advertise the type of information the word carries. So if creatura is asking for adjectives, an adjective like fofa, cute, or azul, blue, will have a key vector that's trained to mathematically resonate or respond positively to that kind of descriptive query.
Okay, so we have the question, the query, and a bunch of potential answers waving their hands to keys. How does the model decide which answer is the best match, the most relevant? This has to be quantitative.
Right, it is. Step 3 is the relevance check, and this is where the math gets critical. The strength of the match between one word's query and another word's key is calculated. Usually this is done using the dot product. Now, for anyone not deep into linear algebra, the simple idea is that the dot product measures alignment. It tells you how much 2 vectors are pointing in the same direction in that high-dimensional space. How similar are their ideas or requests? If the query vector asking any adjectives here points in a very similar direction to the key vector saying, I am an adjective, their dot product will be high relevance.
That makes intuitive sense. It's not just yes, no. It's a score based on how well aligned they are. The better the alignment, the more attention that keyword gets from the query word.
Exactly. And that dot product score essentially becomes the attention weight. This score that usually gets normalized, often using something called the softmax function, which basically turns all the scores for a given query into probabilities that add up to 1. It ensures the attention is distributed properly, saying pay 70% attention to this word, 20% to that one, 10% to this other one, for example.
Okay, relevance established, weights assigned. Then comes the actual transfer of information.
Step 4, information exchange, using the value vector, valor. Once creatura figures out, okay, fofa is highly relevant, the word fofa then sends its value vector over. The value vector is like a package. It contains a distilled version of foca's meaning, maybe emphasizing its cuteness aspect in this context. It's the useful payload of information. And that value vector is then mathematically combined with creatura's original embedding to update it, making it a little bit more cute creature.
Ah, that's a key distinction. Query and key figure out who to listen to, but the value is the actual message being sent. And this whole process, query, key, value, update, is happening for every word, looking at every other word all at once.
Simultaneously, yes. And not just once. This entire dialogue happens within each block or layer of the transformer. When you hear about models having, say, 96 layers, that means this whole query key value conversation happens 96 times in sequence for the input.
Wow.
Each layer refines the embeddings further, allowing for incredibly complex relationships and context to be built up. It's this intense, repeated self-interrogation that makes the models so powerful.
And I imagine so computationally expensive to train and run. All that internal chatter takes energy.
A huge amount, yes.
Yeah.
That's the cost of that deep contextual understanding.
Okay, so we've got words starting as generic vectors, then being constantly refined through this attention dialogue. Query, key, value. Now let's zoom out a bit. If everything is represented by these numerical vectors being pushed around, what does meaning itself actually look like inside this AI brain?
Right, and this is where it gets properly mind-bending, I think, because the answer is meaning is direction and distance. It's all geometry. Inside the LLM, the meaning of a concept is defined by its position and its relationship, its direction and distance to all other concepts in this enormous high-dimensional vector space.
And we have to keep emphasizing the scale here. High dimensional is such an understatement. Our brains are wired for 3 dimensions. The sources mention models like GB3 using, 12,288 dimensions for their embeddings. We can barely visualize 4.
Exactly. And some estimates put the total conceptual space the model operates in at potentially 1.5 trillion dimensions. It's a geometric reality that's completely alien to our intuition. In this space, concepts aren't definitions stored in files. They're purely spatial relationships. If 2 vectors are close together, their concepts are semantically similar. And the direction from one vector to another, that encodes abstract relationships.
This is where that classic example comes in, right, of the vector arithmetic, because this is maybe the clearest illustration of how the machine learns abstract ideas.
It's the perfect example. The model figures out concepts like gender or royalty or verb tenses purely by observing consistent directional shifts in this vector space. The famous one is showing that the vector difference from man to woman is mathematically very, very similar to the direction from king to queen.
Whoa.
That abstract idea, the difference between male and female counterparts, exists as a specific direction in that 12,288 dimensional space.
So the math literally captures the analogy. If you write it out, vector king minus vector man plus vector woman, the resulting vector lands incredibly close to the vector for queen.
Precisely. And think about what that means for intelligence. The model wasn't taught the rule kings and queens are royal, but differ by gender. It just processed billions of sentences and discovered mathematically that these concepts consistently exhibit the same spatial relationship, meaning it emerges from geometric patterns. Concepts aren't definitions. They are geometric relationships.
You know, for anyone listening with a background in information science or library science, this feels like a mathematical echo of things we do manually, like building taxonomies or ontologies, structuring knowledge by defining relationships. Is king a type of ruler? Is it related to queen? But here, the structure just emerges from the statistics of language represented geometrically.
That's a great connection. It highlights both the power and maybe the limitations. It's incredibly efficient at finding these patterns, and it also explains why plugging external knowledge, like human-made knowledge graphs or ontologies, into LLMs can be so effective. Those external structures act like guide rails. They essentially pre-orient the vectors. If you tell the model up front, hey, king and queen are related via royalty and gender, you're giving the initial vectors a nudge in the right geometric direction. It reduces the amount of internal attention dialogue needed for the model to figure out that basic relationship from scratch. You're optimizing the starting point in the meaning space.
So you're basically giving it a map, or at least some coordinates to start from.
Exactly. You're leveraging human knowledge structure to help the geometric search along.
Okay, this is fascinating. We have context being built dynamically through attention and abstract concepts represented by geometric directions. But what about simple, hard facts? Like, if I ask the model, who is Michael Jordan, how does it know the answer involves basketball? If there's no dictionary, where does that specific factual link live? It can't just be context, can it?
That's a great question, and the answer reveals another layer of specialization within the transformer. It seems concrete facts aren't primarily handled by the attention mechanism itself. The research points towards the multilayer perceptrons, or MLPs. These are distinct blocks of computation that sit between the attention layers in the architecture.
Okay, so the vector information flows through an attention layer, gets adjusted for context, and then it hits one of these MLP blocks, like a checkpoint.
Sort of, yeah. And the way these MLPs seem to store and retrieve facts is, well, surprisingly mechanical. The sources describe it almost like a simple electrical circuit, a kind of logical on-off switch.
An on-off switch for facts. Let's trace that. How does the model connect Michael Jordan to basketball?
Okay, so it works roughly in two parts. Part one is detection. This happens in the first layer, or matrix, of the MLP block. Imagine a specific row of calculations within that matrix. Through training, that one row has become highly specialized. It's tuned to detect the simultaneous presence of the specific, contextually refined vectors for Michael and Jordan arriving together. It functions like a logical AND gate.
So it's specifically looking for that combination, not just Michael or Jordan alone, but the pair.
Exactly. The alignment has to be right. If, and only if, the incoming vector flow contains that specific activated Michael Jordan concept, then that particular row, that artificial neuron, essentially fires up. It gets a positive value. It switches on end. If the Michael Jordan concept isn't strongly present, that neuron stays dormant, OFF. It's a very precise trigger.
Okay, the Michael Jordan detector is own. How does the basketball part get added?
That's part two. Addition. There's a corresponding column in the second matrix of that same MLP block. And through training, that column has come to represent the vector direction associated with the concept basketball, or basket. So, when the Michael Jordan detector neuron in the first matrix fires on,
It activates the add basketball instruction in the second matrix.
pretty much, the system is set up so that activating that specific row causes the basketball vector information from the corresponding column to be mathematically added to the Michael Jordan vector as it passes through the MLP. The output vector is now the original Michael Jordan vector plus the basketball vector components.
Wow. So it's not looking up basketball in a list of Jordan's attributes. It's literally changing the mathematical direction of the Michael Jordan vector to include the direction of basketball.
Exactly. It's embedding the fact directly into the vector's geometric position. This is different from attention, which is about relating words within the current sentence. The MLP seems more about injecting established world knowledge facts, like if you see Eiffel Tower, make sure to add the vector components for Paris's and iron structure. It ensures the vector reflects known attributes through these quick conditional additive operations.
That really demystifies factual recall. It's not memory like ours. It's a cascade of these specialized, trained logic gates altering the vector flow based on detected triggers. It's incredibly mechanical.
Very much so. A vast network of highly specific AND-DAND circuits, basically.
All right, let's tackle another concept that just breaks my brain trying to visualize it. We keep talking about this massive 12,288 dimensional space. But here's the thing. How can an LLM possibly store and differentiate way more concepts, features, and ideas than it actually has dimensions? That seems impossible in our 3D world.
Yeah, this is where our physical intuition completely fails us. Our 3D experience tells us quite reasonably that if you have n dimensions, you can represent n independent features or directions, and that's it. Length, width, height. 3 independent things.
Right. You can't cram 100 independent concepts onto just 3 axes without them all blurring together into mush.
Exactly. But the math and the way these models work shows that this rule gets completely shattered in very high-dimensional spaces.
And the phenomenon that allows this is called superposition.
Superposition, yes. Or sometimes you hear about polysemanticity of neurons, meaning one neuron participates in representing multiple different concepts. The core idea is that in these incredibly high-dimensional spaces, like 12,000 plus dimensions, you can pack an exponentially larger number of distinct concepts or features by having the representative vectors be almost perpendicular or quasi-orthogonal.
Almost perpendicular. Okay, what does that mean practically? Like the angle between the vector for is red and the vector for is fast might be like 89 degrees or 91 degrees instead of a perfect 90?
Exactly that kind of thing. They're not perfectly independent, which would be 90 degrees, but they're so close to perpendicular that they interfere with each other very little. Think about it. In 3D, if two lines are nearly perpendicular, they still look pretty distinct. Now imagine having 12,000 dimensions to play with. Vectors can be incredibly close in angle, maybe differing by only a fraction of a degree, and yet still occupy fundamentally different slices of that vast geometric space.
So the sheer vastness of the dimensionality allows concepts to be packed incredibly tightly without catastrophically overlapping.
Precisely. It allows for an information density that's just impossible in low dimensions. This means a single feature like plays basketball, or is a famous athlete, or is blue doesn't need its own dedicated dimension or its own dedicated neuron.
Ah, okay. So you don't have a basketball neuron and a baseball neuron.
No. Instead, the model represents potentially millions of distinct features as specific combinations or superpositions of activity across many neurons or dimensions simultaneously. A feature becomes a particular pattern of slight activations across a wide range of dimensions, where each dimension might also be participating in representing hundreds of other features in slightly different patterns.
That sounds incredibly efficient, but also incredibly fragile, like tuning a radio to an extremely precise frequency.
That's a fantastic analogy. The same airwaves, the dimensions neurons, carry thousands of signals, features, superimposed on each other. Only the exact mathematical tuning, the precise calculations in the attention and MLP layers can isolate the signal you need. The benefit is immense storage density. The drawback is that if the calculation is just slightly off,
You might accidentally pick up interference from a nearby frequency. You might pull in a fragment of a related but incorrect feature because its vector was almost perpendicular but not quite perfectly ignored.
exactly. That's the inherent risk and trade-off of superposition. It enables this incredible density, but it demands absolute mathematical precision. A tiny error in calculating vector alignment could cause the model to incorporate the wrong superimposed information.
Which might contribute to some of the weird errors or hallucinations we see sometimes.
It's certainly a contributing factor, yes. It highlights that the AI is operating using a kind of geometric logic that's just fundamentally different from how our brains seem to organize information. It's solving storage by embracing this weird, high-dimensional multiplexing. Okay, so we've covered how words become vectors, how context is built with attention, how meaning is geometry, how facts are stored, and how it packs info densely. To round out this picture of the LLM brain, we need to talk about how it all gets set up in the first place. Learning. We tend to anthropomorphize it, right? The AI learns history or learns to code, but the sources paint a picture that's, well, much less romantic. It's basically brutal, relentless mathematical optimization.
Right. Let's start at the beginning. Before training, the LLM is basically useless.
Completely, utterly useless. When an LLM is first initialized, all its internal parameters, the billions of tiny adjustable knobs that control the vector transformations, the attention weights, the MLP gates, maybe 175 billion parameters in a model like GPT-3, they're all set to random values, small random numbers. If you try to get a response from this untrained model, you just get gibberish. Total nonsense.
So the entire goal of the massive, expensive training process is just to fix that randomness, to turn the knobs away from random settings to useful ones.
That's essentially it. The goal is to find a configuration of those 175 billion knobs that makes the model good at its core task. And to measure good, we need one single number, the cost function or loss function.
A cost function. Okay, what does that represent?
It's the model's error score. It's a mathematical formula that calculates, on average, how badly the model did at predicting the next word in a sequence compared to the actual next word in the training data, which might be trillions of words from the internet, books, etc. A high cost means lots of wrong predictions. A low cost means the predictions are getting close to the real text it was trained on. The entire objective of training is simply to adjust those billions of parameters to make that one single cost number as low as possible.
So it's not trying to understand in a human sense. It's just relentlessly trying to minimize its prediction error score. It's pure optimization.
Pure large-scale optimization. Oh. And the main technique used to do this minimization is called gradient descent.
Gradient descent. The sources use a great analogy for this involving hills and valleys.
Yes, it's the best way to visualize it. Imagine that cost function, that single error number, defines a landscape. A vast, complex landscape with mountains, hills, and deep valleys. High points on the landscape represent parameter settings that give a high error score, bad performance. Deep valleys represent settings that give a low error score, good performance. Training starts by placing a ball somewhere high up on this landscape. That's the initial random state. The goal is to get the ball to roll downhill into the deepest valley possible.
Okay, but with 175 billion dimensions defining this landscape, how does the model know which way downhill is from any given point? That seems impossibly complex.
That's the magic of calculus, specifically an algorithm called backpropagation. It's the engine driving gradient descent. When the model makes a prediction during training and the cost function calculates the error, nope, you predicted cat, but the answer was dog. Backpropagation does something remarkable. It sends that error signal backwards through the entire network, layer by layer.
All the way back from the output to the input.
All the way back. And as it propagates back, it uses the chain rule from calculus to calculate for every single one of those 175 billion parameters exactly how much that specific parameter contributed to the final error. It figures out the gradient, which is essentially the direction of the steepest uphill slope for that parameter.
So it knows which way is up, more error, and to
Go downhill.
you just take a small step in the exact opposite direction of the gradient. Backpropagation tells each of the 175 billion knobs. Okay. To reduce the overall error slightly, you need to nudge yourself a tiny bit in this direction. All the parameters get nudged simultaneously, and the ball rolls a tiny bit further down the slope.
And this process, calculating the error, backpropagating to find the gradient, nudging all the parameters, just repeats. Trillions of times. Over weeks or months, using massive amounts of text data and computational power. Step by tiny step, the ball rolls downhill. This really should demystify the term learning in this context. There's no conscious thought, no aha moments. It's just this relentless, mathematically guided descent towards parameter settings that minimize prediction error on the training data.
And it doesn't even need to find the absolute bottom of the deepest possible valley, right? Just a pretty deep one.
Exactly. It needs to find what's called a local minimum, a valley that's deep enough for the model to perform well, to generate coherent and useful text that matches the patterns in its training data. It might not be the theoretically perfect global minimum, but it's a configuration of parameters that works very well. The optimization stops when the ball settles into one of these good enough valleys. #outro.
Wow, okay, that's quite a journey we've taken. From words starting as these identical generic number lists, through that constant internal dialogue of attention-building context, exploring meaning as pure geometry in this crazy high-dimensional space, seeing facts get bolted on by these little logic gates, understanding how it crams information and using superposition, and finally, realizing that learning is essentially this massive optimization process, just rolling down a mathematical hill to minimize errors. It really does strip away the magic and replace it with mechanics.
It absolutely does, and it forces us back to that fundamental question. When we say an LLM understands something, what do we actually mean? It's clearly not understanding in the way humans experience consciousness or subjective awareness. It seems to be understanding as the successful construction of a geometrically accurate and probabilistically sound representation of semantic relationships. An understanding derived entirely from minimizing mathematical error over vast data sets.
And thinking about it geometrically, like we have been, that leads to a final, kind of provocative thought, doesn't it? If meaning is geometric position and learning is finding a low point on this error landscape, what happens if the ball doesn't roll into the perfect valley? What if the calculations are just microscopically off sometimes?
Exactly. This brings us right to phenomena like hallucination. When an LLM generates text that sounds perfectly confident, perfectly coherent, but is just factually wrong, completely made up. Are these hallucinations necessarily bugs or flaws in the traditional sense? Or could they be seen as almost expected outcomes of this optimization process?
What do you mean? Like it's just a natural consequence of the math?
Potentially. Think about that ball rolling downhill. It settles into a local minimum, a valley that represents low error on the training data. But maybe that valley isn't the globally correct one. Maybe the geometric position it found for a concept is extremely close to the truth, works 99.9% of the time based on the data it saw, but it's subtly distorted. A hallucination, then, might just be the model confidently reasoning from within that slightly warped but mathematically stable local minimum it settled into during training.
So the hallucination isn't necessarily the model breaking. It's the model perfectly executing its learned logic, but from a starting point that's geometrically slightly off base due to the optimization landing in an imperfect spot.
That's the provocative idea, yes. It suggests that a certain degree of potential error or misalignment might be inherent in the very process of learning through gradient descent in these incredibly complex spaces. The system is accurate relative to the minimum it found, but that minimum might not perfectly map to reality.
That definitely gives you something to chew on. the ability of these systems to weave together the geometry, the logic, the attention, the optimization, it's still astounding, even when you see the mechanics. But understanding those mechanics reveals that the journey into the AI's mind, or maybe its geometry, is really just beginning. There's so many more questions.
Absolutely. The deep dive definitely continues.